I'm going to get started now because we'll do the standard rigmarole, and that'll give everybody a minute more to come in. All right. So this is actuarial modeling from a software engineering perspective. So I've been thinking about this presentation for 15 years, and so I'm really kind of excited to give it. So thank you to our sponsors, Standard, Coherent, the Gunja Group, and Post-it. I think this is a great conference. I've learned a lot of cool things today and reinforced some other things that I knew, and it's fun to see other people's perspectives on how I view things. Antitrust law things that we've seen in all the other presentations. I am talking about mentioning particular vendors. So if anybody wants to chime up and say, hey, you probably should say that, keep me honest. But other than that, let's get started. So before I even get started, I want to start with what I want you to know off the top. All the lack of innovation and inability for actuaries to modernize, basically our pain, have known causes from a software engineering perspective. So there's no research that needs to be done. There's nothing. All the problems have been solved. The root, we have one root source of our pain, and that is that we have a deep coupling of data and logic from the highest and lowest level of our actual technology stack. So the whole point of this conversation is to show you, is to relieve this pain and show you how to solve it through basically abstraction and modularization, because our end goal is to make sure that our models are loosely coupled and tightly cohesive, which I will define next. The other thing is that when it comes to modernization, what I find is a lot of people want to throw technology at the issue. Oh, modernization technology issue, which is throwing it at the back end, going towards the cloud. But what is really important is to start focusing on the front end, on the software and the people. That's where 95% of the innovation needs to go. So, and these processes will allow us to automate model governance, reduce model risk, and ultimately make it so that actuaries can innovate. But until we get rid of this coupling, we can't do that. So let's define what I mean by tightly coupling and cohesion. So tight coupling is about how things are interrelated. So look at the glass here full of all these different liquids. Imagine we had a drinking game at a bar, and I said, all right, I want you to suck out only the red liquid. Well, those things are very in there. You're likely going to take other colors in there because all that is tightly coupled within that liquid. What does it mean to be loosely coupled? Think about Legos. Legos have different colors. You can sit there and you can add blocks and do different things together, and they're built to be loosely coupled, so you can build all kinds of things and sort them. That's exactly what we want in our software. Cohesion. Cohesion is about how things are related. So if you look here on the right, you see I have a giraffe's head on a monster truck with some little data table. Those have nothing to do with each other. So the cohesion is loose. What we want is to be tightly coupled, tight cohesion, which means everything has a purpose. It's nice, it's tight, and it exactly does what it needs to do. Because coupling leads to very buggy code that breaks, and poor cohesion leads to loose cohesion leads to spaghetti logic. So we want to avoid the red, is what we have today, and we want to move ourselves to the green. So how do we get? Yes.
You're not sharing your slides with us.
Oh, that would be a problem. Sorry. I thought it was.
It was coming like an inspirational.
Yeah, you were describing them very well.
It was cool.
We had images in our mind.
Can you see them now?
Yes, we can see them now. Thank you.
Okay. Sorry. Here I am going through this. Okay, sorry. So you got it. Lego's good. Transmission's good. Liquid's bad. This is just kind of chaos. Okay, sorry. Thank you for that. Moving on. All right. So Milliman did a fostering innovation study. And I didn't agree with what their solutions were for innovation, but they immensely described the pain. Employees, right, senior managers had to control all the innovation that happened, which your perspective on what needs to happen is vastly different between where you're sitting at the top versus where you're local, where pain is happening. You know, nobody was able to, bosses wouldn't allow people to innovate because they were afraid of, they were afraid that things would break. And everything is so tightly coupled together across the organization. If one person changes something, it breaks the entire system. So actuaries aren't allowed to innovate. So they're basically stuck. So let's see what the sources of pain are and why we cannot innovate. So basically, we lead to data and logic coupling leads to very poor change management, which leads to a fear of change, which is where our extreme modeling challenges come from. Okay, so here's something that we must understand is that our models are like black holes. You're either running a model, you're building a model, or you're governing a model. So everything runs to a model. So what I want you to understand is organizations don't create their systems and process that people use. They don't say, this is my dream, I'm going to go get these people, and this is what I'm going to do, and it's all going to work. What happens is your systems and processes have holes in them, and then you decide based on those holes who you're going to hire and what skills you need. For example, assume you have processes A, B, and C, and A is automated, and C is automated, and B is not. What is going to happen as you scale? Well, you're going to get all of these people. You're going to hire people to coordinate between the automated processes and the manual processes. So all of your people will start to aggregate around these processes, around the manuals, around the coordination. And as you scale, you'll have more people to help with the coordination, and those people will need managers, and then you'll need managers to manage the managers, and so the whole organization is based around this coordination. So solving the problem with data and logic coupling will also help make the organizations run much faster. And by the way, if you want to really see a good presentation on this, I suggest you watch Brandon Burns' why do you care about microservices on YouTube? Fantastic presentation. Okay, so the state of actuarial modeling, why things are so sticky and brittle. So one of the things I want you to really get a sense of is why we're in the situation. Because if you look here, this is a busy slide, but what I really want you to see here is in the bottom left, that most actuarial software was built before the internet. And that had its genesis before the internet. The only ones that really didn't were Atlas or PathWise. But everybody else pretty much had their genesis there. And the reason, what happened was before the internet, systems were large and monolithic, and everybody did things in one system. But as the internet happened and it scaled across the globe, they no longer could keep one in one application. Like think about Amazon.com. It's not one application. It's what they call microservices, a whole bunch of tiny little, very, loosely coupled, tightly cohesive little modules that aggregate together for your entire experience. So they're not managing that as one big thing. But the problem is the problem is that the front of our actuarial software is built based on pre-internet type of stuff. So all of our modeling software is built with a monolithic idea. So, and monolithic leads to waterfall type of a project management. Post-internet is to build things in small pieces and then have them work together. So I want you to understand the first thing to modernize is to modularize with abstraction, because that's what's required to do agile programming, to do agile type of stuff. I actually hate that word because I think it's overused. But the problem with actuarial science most of the time is they call it agile, but what it really is it's agile waterfall, which is the worst of both worlds, because now you get the bureaucracy of the morning stand-ups along with the slow things of waterfall. It's exactly what we don't want, because when agile meets waterfall, waterfall always wins. So we got to figure out how to modularize and abstract. That's the point of this thing. So let's get back. Let's go back home here So something we all recognize. And let's go to Excel, because this is a great analogy of what we need to do in our modeling platforms too. So if you look at old school Excel here, right, and you look at this equation, B times B3 times B4, our data and logic is coupled together, right? Because I also have the location of our data coupled with it too. So this is really bad because it's really hard. It's really hard to change. If I want to reuse this logic, I basically have to copy it, which means then I have to manage it in two spots. So then in, let's say 2019 or 20, Excel introduces the let function. Well, this is better because now I'm able to separate my data from my logic. But if you look at this let statement, it says let V equal B2, let Q equal B3, let CF equal B4, and then V times Q times C4 is your result. So it's coupled the location and the data to the variables, but you've been able to separate your logic from your data, but your data is still coupled to your variables. So it's better. That's why it's in yellow, but it's still not as far as you want to go. The last thing is, they introduced the lambda. Now the world is right again, because now my data is completely decoupled from my logic, and then I can put my data in from anywhere into my function and get the same result. That's what I want. And by the way, as we're talking about links, and in the previous conversation, tight coupling is workbook links. Like if you can avoid those things, that is what makes actual processes extremely literal. And loose coupling is using lambdas, the greatest invention that, they're awesome. So effectively, we need to make that same, Excel was our inspiration for, I remember when I was working at ARC, they said, Prophet kind of works like Excel. And so, okay, we kind of need to have our actual platforms to kind of follow that same type of mindset. So now let's pretend that we are in ALFA or ALFA or Prophet, right? And in ALFA, they call the variables that you find function variables. I love reading documentation because a lot of times you can figure out what people are saying by the way they document. So a function and a variable is two separate concepts. Define them as being coupled together. So you already know you have a problem. The other thing is that what happens here is all those function variables can see each other. So so that's essentially the same thing as each cell being able to say every other cell. It's hard to decouple and deal with that logic. So what we need to do as a profession in our modeling platform is separate the variable from the function and reduce the scope, and then you're able to deal with things and modularize things and use them in smaller units. So that's effectively where we got to go. So those two, so Excel and this are exactly the same thing. We want to make an analogous type of move forward to be able to help us modernize. Okay, so the other thing we need to know is that change management reigns supreme, right? A model describes the behavior within an environment. Your assumptions and data describe your environment. Your logic is your behavior within that environment. So to truly show how the things are behaving properly, you need to show it through change management. So change management needs to reign supreme. Now, back to George Box. I hate this saying because, again, I think it's overused, but all models are wrong or some are useful, because we need to add a corollary to that. Most precision on future forecasts is false, and so we have an overconfidence in forecasted results. There's really only 4 actuarial numbers, right? There is who cares, there's that's interesting, there's I should probably look into that, and there's ruh-roh shaggy, but that's it, right? And so really what we need to think about, this is a whole other hour-long presentation, we really should be focused on like stochastic accounting, where rather than saying we're doing the expected value, we should have expected value and confidence around it. But the reason we are so overly focused on numbers, because it really has to do with compensation, right? If you get a 7.49 IRR on these products, you don't get a bonus. If you get a 7.5, you magically do. Well, in reality, the precision you have on your future calcs, there's no difference between those. So we come up with these arbitrary cutoffs due to things outside of what we're actually doing. So that creates us a huge problem. That means we have mixed priorities. So that means that everybody is focusing on features and products first because they want to be able to model all the fine minutia of everything to get this false precision. And then they want to get to that false precision really fast. And then we worry about how we're going to change this and model and governance thing. That is completely wrong. We should do the priorities exactly the opposite way. I don't want you to talk about your software and all the whiz-bang things it can do until you talk to me how I can manage it, I can change it, I control it, and I know every aspect of it, anything. Then you can tell me about how fast it is, and then we can worry about how much precision and what we need to do. If I can get in the ballpark and get the right behavior and things move in the right direction, that's what I should care about more. But I really, to understand the behavior and describe the behavior, it's really about change management. Does this thing work the way you anticipate it to work within the environments that you're describing? Okay, so let's go a little bit lower and find the source of some problems. So one of the things is that we got to understand is that because our actual software couples our data and logic together, they manage it together, which is horrible. It's like managing a spreadsheet in SharePoint, right? But we should realize that data is dead. And that's maybe an over exaggeration, but data is kind of fit for purpose, right? You're not doing anything with your data. You store it off. It might have different dates of applicability, but you're basically done with your data. That's your environment. That's what you're assumed to be true. But your logic is alive and breathing. That's how it behaves. And so you're constantly modifying this as you think about how things should behave, and you're constantly refining it. So they should be managed vastly differently, right? You should have your code in Git, and it should be able to use all modern tools, and your data should be somewhere else. You should not be storing your data in your model and then trying to manage all that together. That's just a recipe for disaster. So let's talk about software complexity, called cyclomatic complexity. What you need to do is you need to count all the independent paths, and loops and branches and decisions within your code, because the more they have, the more complex it gets. So this is straight out of ALFA, right? You see the problem where I have 48 lines of code between two different variables, and the only thing that's different is the global variable. So basically, if we looked at the cyclomatic complexity of, let's pretend this is the only two variables I have, the cyclomatic complexity is double of what it needs to be. If all I had was a simple function, I could put that redundant code in that function and reuse it. And so this is really bad. So I'll talk about the consequences of this later, but this has huge consequences to the difficulty and governance and testing of actual software. Okay, so the problems that leads to are, right, if you have no concept of function, you can't reuse logic, right? And so if you can't, then you have redundant logic proliferated throughout the model. So that is automatically increasing the complexity and the difficulty of governance. And if you go to change one, you're likely not to change the other. And this means that because everything is tightly coupled together, that you can only do end-to-end testing. Which end-to-end testing, when you have redundant code, you might think, well, I tested how that vol variable worked. Well, no, you tested one of them, but you didn't go down the branches of the other. So it becomes very, very hard to understand what this is doing, and it becomes very, very highly error prone. And furthermore, it becomes hard to collaborate because you have to know where all those are at. You have to know where all that redundancy is at. You have to know to go change those things, which makes the comprehension of the model much harder. So one of the things that we've got to change is we've got to update our actual standards. If you look at ASOP 23 and 56, they're more about wannabe data scientists. We need to introduce software engineering standards, and we don't even need to do anything ourselves. IEEE has plenty of these engineering standards. We can just go grab them, and we can then just filter and tweak for what is applicable to us. But the idea that our modeling has no standards in engineering, or virtually nothing, is a lot of our problems. So the problem is with tightly coupled data, we can only do end-to-end. So that means we really can't do any automated testing. We can maybe do regression testing, but we can't really figure out how the different units are behaving, and that's required because we have so much redundancy. And the other thing is that the more redundancy you have and the more conditions you have, the more it takes people to learn. And the project can only go at the speed at which people can learn. So that's some of the problem here. That's why modernization is more likely a people problem than a technology problem, right? Another way of putting that is projects can only go at the speed at which people can comprehend it. And so given the redundancy and the coupling, our models are very, very hard to maintain. So how do we relieve your pain? So we got to decouple and we got to abstract. So let's talk about how we decouple this. So before we can talk about decoupling, we need to talk about different programming paradigms. So the structured paradigm is what actuaries are most familiar with. That's what most of our stuff does. That's what we're doing in VBA. And essentially, that's just you put your data in global memory, you have a task list within functions that you want to do, and you go through those tasks, and when you get to the bottom, you're done and you get your output. The second paradigm is object-oriented programming. And what that does is it's programming in terms of responsibility. Like think of like your team at work, right? You have a manager and he has these different classes. These different classes are going to communicate together just like individuals on the team. They're going to do these tasks back and forth until they finally get to their final result. So object-oriented programming is programming in terms of responsibility. The one we really want to focus on is functional programming. This is where, think about it like a matrix. You want to basically start with a matrix, and then you want to use different transformations to eventually end up with a final result. And so we really need to consider more of a functional programming paradigm. So let's dive in deeper, because this is essentially, there's a reason that I used Excel as the analogy to what we need to do, because lambdas are basically functional programming in Excel. So I'm going to use those as an example here to show what we need to do in our modeling platforms. So the first thing about pure functions is that that when I give you two parameters, I will always get back the same result. Which is good, because if I'm sitting there and doing something with a global variable and I give you two parameters, if that global variable change, it's going to cause what they call a side effect, and that's going to make it harder to test. So purity is a beautiful thing. Immutability. So the other nice thing is once you declare a variable of value, you can't say like A equals 1 and then A equals 2. You get A to be equal 1 and then you're done. Otherwise, you would have an error. So this again allows you great control. Functions are first-class citizens. What that means is you can declare something a function just like you would an int or double or any other type within the language. Which leads to the last one. Of the next thing is higher order functions. So functions that can become parameters of functions. Functions can be returned to functions, and life is good. Functions can be composed, and the only consequence of this is that rather than doing a for loop from I equals 1 to n, you can't do that because you can't change the value of I. You have to loop through recursion, which is not the end of the world. Anything you can do iterably, you can do in recursion. It just takes a little bit of rethinking. Okay, so why is this important? Because if you saw that redundant code, the reason it was is because there is no concept of function, there is no concept of scope, so we have no ability to reuse our logic. So that means because of that and everything is global, we can't define things into single behaviors or units, which means we can't use modern software testing. And so that's the first thing we got to do, is we got to modularize and put this thing in the small pieces so that we can actually do the unit testing like the tools would work. Because, and then in our world, basically a single behavior would probably be a function. It doesn't necessarily have to be. And then when you have multiple behaviors working together, that's called integration testing. And then what actuaries do is end-to-end testing. End-to-end testing is even hard if you have all that redundancy and you have and things like that, because you don't necessarily know whether you went down a loop or down the right path, or maybe you go down another path and you come up with a completely different part of the code. It's very bad. So because when you're doing testing, there's no maximum way of doing it, but you either want to look at the code coverage, how much of the code have you covered, or you want to look at the branch coverage. And this becomes exponentially harder as you have redundant code all over the place, because you might think that you've tested something, but you actually haven't, because it exists in multiple places. So I take you back to this again of like a ALFA Prophet type of view of the world. And before I showed you, hey, we need to separate the function from the variable. We need to reduce the scope of the variable. Where scope, I think I forgot to explain that earlier. Scope is where you can see the variable. So if it's global, everybody can see it. If you move the scope down, that means less and less people can see it. And the reason that you want to do that is because you effectively want to be able to then create testing doubles so that you can have that unitization. That is fundamental to key. Without unitization, you can't have the intermittent test. You can't have the unit test. And so then governance becomes extremely hard. So there are different types of testing doubles. There are stubs and there are mocks. Mocks are when your code changes the dependencies. So pretend your actual model feeds into a database and you want to make sure that database got fed properly. That's a mock. Actuaries are going to be using many mocks. But stubs is taking inputs and then changing those inputs in different ways. And there's different types of stubs. There's a dummy where you just say, well, I'm just going to give you a hard-coded value, so I make sure you go down a path. Whereas a stub might have a little bit of logic in it to better replicate it. But what it is, it's a simplified version of the actual thing, so that you control what it's doing, so that you can better test those units. Right. So then what you get is, then once you've modularized these, you get a nice little unitization of your model, just like a Tetris game. And then your little red ones can be the little stubs that you use to be able to reduce the complexity and make sure that in your unit test you can actually understand what the model is doing, as opposed to building spreadsheets and having to do the end-to-end stuff and all that stuff. So this is exactly what I have done. So if you look on the left, this is an alpha variable where all the brown variables are global scope. All the green variables are local. And then what I've done is I've transformed that into a lambda expression, so that basically I move the scope of those variables down, and then I can basically build back up in that Tetris I saw you in the previous one of the different functions, so that I can do that. So this is great because now I've modularized our alpha model, so that decouples the data from the logic. The problem is that doesn't necessarily make the logic cohesive. So this is only one half of it, because in software engineering, a lot of what they say is you want to make your test robust to refactoring. What that means is I want to be able to move and change how it behaves, but I don't want to be changing interfaces all the time, because then that will break my test. Well, the problem is, if you just did a straight change like this, what's going to happen is you're going to decouple that data, but it's not necessarily going to be cohesive. So when you figure out, well, I need to put this variable in this function and that variable in that function, you're likely going to break it. So we need to go to learn how to not only decouple them and make them smaller, we also need to learn how to make them cohesive. And just by the way, if you want to know how to do this, this can be automated through a Python library called Lark. But anyway, moving on. So now let's make models more cohesive through abstraction. So abstraction comes in two flavors. It comes in hiding implementation details to manage complexity, and then generalizing those details. And the key here that is important is information hiding. So when you talk about things in abstraction, right? For example, if we talk back about the actual present value of a cash flow, right? You can say, I have a cash flow, I have a benefit. Oh, it's cash flow. Sorry. I have a cash flow, I have a decrement, and I have some type of discount. Right? And I can talk about that. I can talk about that calculation without ever mentioning, well, is it a spot rate? Are we dealing with a forward rate? Are we dealing with just lapse rates? Are we dealing with mortality rates? I don't have to talk about those details. I can just say, hey, it's a decrement, it's a cash flow, and it's this and it's that. So I'm hiding those details from you, and that's how you're able to comprehend more, be able to do more with less information. So a major part of implementation of abstraction is implementation hiding. And so that's why it's so important. If all our variables are global, you have no ability to abstract because you have no ability to hide. That's their fundamental problem. So there are three types of abstraction. There is data abstraction, which is making representations of your data the same. So for example, in an actuarial context, you never want to read from a table. You always want to read from a view. That way you can change up your tables, but you can keep your view, the same. So if you're reading from tables, you're doing it wrong. Procedural and logic abstraction, that's really what we're talking about when we are building classes or functions in Python or ALFA or Prophet or Axis, that's really your procedural logic. And then there's configuration abstraction, which we don't talk much about actuaries, but where you'll run into that is like doing a data transformation, right? Most of what you're doing in that transformation is making sure that the configuration is the same, that, hey, that this product is using this table and is using these values. So it's about abstracting configuration so you can change the configuration of your model without doing anything. So another place to think about this is, this comes important, right? A lot of times we store our data in our models, right? Our mortality tables and all that. Well, you should never be using your production data for testing, because then you're just testing the happy path. And then what's going to happen is you're going to go production. The admin system is going to produce something new because it had some quirky quirk, and your thing is going to break right during production because all as you tested with the happy path and the things that worked, as opposed to being able to configure and put new data in that will test your code coverage and to test your branch coverage. So we should not be doing that. We're actually creating very risky, brittle models by doing that. But it's anyway. So moving on. So let's talk about abstraction here in more detail. So this is an object-oriented version of abstraction. So on the left here, we have modularized our different shapes: our circle, our rectangle, and our triangle. And so all this you're doing when you're abstracting, you're saying, wait, these circle, rectangle, and triangles are just shapes. And these shapes are responsible for calculating the parameter, the area and parameter. So essentially what you're doing is you're defining a set, and you're saying, what is the responsibility of that set? And then your inheritance is always saying, okay, what classes actually belong to that set? And so that's an is-a type of relationship. So a circle is a shape, a rectangle is a shape, a triangle is a shape. And that's how to think about these things. All right, so moving on. So now when it comes to relationship, there is only two. There's a is-a or a has-a. So you are a shape, you are a triangle, or it's composed of something. It has a thing. So a car is made of elementary shapes like tires are circles and the hood's a square. So an inheritance, loose cohesion would be the saying that a car is a shape. Yes, it does kind of have a shape when you compose it all together, but is a car really an elementary shape? Probably not. Can in some modeling aspects you kind of maybe pull that off, and others you definitely can't. So it's not very cohesive. The other thing is on the right that you want to see that's really important is if you look at, let's pretend that I'm like, man, I don't want to bother with building a circle class and a triangle class and a rectangle class. That's just too much work. I'll just create this class called shape, and I'll just put all these variables in this thing called shape, and then I will just call one of these functions when I need to call the area for each one of these. Well, this is tight coupling. because now I have all these things into one class, and it's doing too many things, and I have to, well, what if I decided to leave out the length? And in this case, I use the radius as the length when I'm talking about a square, but I use a radius for a circle. And so you get this cohesive problem. And the one thing I want you to see is the tighter the coupling, the more things you try to include in the shape class, the looser the cohesion, because you're doing more and more unrelated things. Because the area of a circle has nothing to do with the area of a square, even though they're the exact same concept. So, and this is exactly what is happening to us in our actuarial software when all our variables we're defining these models are the same. So, one more thing we need to think about when we think about actuarial modeling software. They are not actually programming platforms. They are domain-specific languages. Just as SQL is a domain-specific languages for dealing with databases, so is Moody, and all the Moody's and ALFA and Prophet and Atlas, they're all just domain-specific languages to help simplify and focus on what actuaries need to focus on. Right? They do not have all the general purpose stuff, such as, like, you know, having to deal with pointers and C++ and all these other stuff. It's domain-specific languages are abstractions that help hide the unnecessary details of what you want. And they only expose the domain's concepts. They do have constraints, but to make things easier for you. But my problem is you got to understand what features you need from a language versus what features you don't. Like, by not providing this function, you oversimplified something. But you remember when I talked about the standards, I didn't show didn't mention the picture at that point with the whack-a-mole. The problem is, if you don't give us enough features to handle some of our issues, then all of the issues, you whack the mole and they're going to squeeze somewhere else. So essentially what happens is, by not providing us functions and a functional programming type of idea, you've hit that mole and you've made a whole governance nightmare, because now we have to deal with all kinds of redundancy in our code and all kinds of overly complicated logic because we don't have something as simple as reusability in a function. That's really, really bad. So one of the other things that I think that actual software fails at is understanding that actuaries need to be working at different levels of abstraction. So a software developer is probably working at the bare metal, right? Because he's working with the programming language. Your modeling and hedging actuaries are usually pretty good at programming, so they're a layer above the metal. But then our pricing actuary, he's going to be a little bit above that. Our valuation actuary is going to want to be able to talk larger than that. And our ALM actuary, he's not going to really care about the cash flow of an individual policy, right? He's going to care about the overall patterns. Same thing with the RM, the overall patterns of the organization in terms of assets and liabilities. So he should be able to work with the model at a much higher level. But our modeling platforms all assume that everybody is the modeling actuary. It's one of my major problems with Axis is all the batches. They're just, it's like, can you not abstract that a little bit and allow me to have layers so I can better deal with my problems, as opposed to having all these batches interrelated together and I go figure it all out. So this is one of the failures, I think, of all of them, is not allowing actuaries to talk more at the level and the language that they need to. Okay. So let's get into the abstractions mechanisms of the actual models that we have. So I look at ALFA and Prophet the same. They actually started from the same seed. Back in the 90s, Deloitte and Milliman had a joint venture, and they kind of made the software together. Eventually that dissolved. One went one way, one went the other. Milliman became ALFA, Prophet went to Deloitte, and through their evolution. So they started from the same seed, so they essentially have the same problems. They're almost identical. They both transform the DLLs to C++. In Prophet, you're going to call it a library. In ALFA, you're going to call it a formula database. In ALFA, you're going to have user-defined variables. In Prophet, you're going to have extended formulas. In ALFA, you're going to have a category tree. In Prophet, you're going to have indicator expressions. But they're really the same. They're really the same exact concepts in both software. All right. So all actuarial software is going to get this right. This is the ALFA's view of the world. And by the way, as much as I'm about ready to beat up on ALFA, one of the best things about it is they have this document called the Actuarial Structured Document, where it goes through conceptually about how their software works and related to actuarial science and accounting. It is fantastic documentation. You can learn a lot about just counting and everything from reading that. So that is worth a read if you can get your hands on it. So anyway, but in general, you know, this is ALFA view, but a module is like a liability or an asset. So it is a relationship which produces a financial transaction. And there are three types of financial transaction. It either flows into the income statement, it either doesn't flow, such as target surplus, or it's structuralist that just bypass and it's just something you put in the output for later details. And then that composes up a financial statement of a balance sheet or an income statement. So all actuarial software has these abstractions in common, but I kind of wanted to relate this in terms of what, but it's at the module level that all thing goes awry. So what we're looking at here is pictures of ALFA. So if you can look at this, this is really, you know, rather than me describing this, and your shape in this concept is your base liability. So you would read this hierarchy as your base liability is a deferred annuity, which is an index deferred annuity. This is and you can even see this. So yeah, so the shape would be where the is equivalent to where it says concrete is no, and then your actual implementation, your circle, triangle, or square is where your concrete is yes. So that means that it's an actual type that you've implemented. Okay. So furthermore, in Prophet, they have this exact hierarchy, but they call it an indicator expression. So you're going to have this indicator expression called base liability and deferred liability, and is index, and then so basically this hierarchy is the same. And then Prophet is also going to have categorized variables just like this. And now it's been 15 years since I looked at Prophet, but I was scarred by it. So most of these details I remember were scrutiny back then. But what I don't remember is where is the varies by concept within Prophet. I think it's embedded within the Prophet tables, because when you go to a Prophet table training, the first thing you will do is you will spend 2 or 3 days learning how to make a you will learn how to make the Prophet tables to feed the systems. But in ALFA, the varies by is with the variables, and this has they have similar concept. And I want to compare, and even if that's not true, let's pretend that it is, so because I want to compare and contrast that way. So if you look at this hierarchy of types, you should notice that these are very broad types, right? These are very high level. It's a deferred annuity type. So what that means is that an ALFA model is very tightly coupled because these are type. Because the only way, because below the liability type would be the concept of a product type, right? I have product A, product C, product D. And the only way that you can handle that is with a lot of if conditions. So an ALFA model is going to be very, very tightly coupled because you're going to be dealing with these broad type of categories with if conditions. Okay. And so let's now talk about Prophet. Okay. So let's assume, like I said, I think it's true that the varies by is within the table. So how you know how to read the table is by refining that indicator expression, essentially making that hierarchy more refined. So what you're doing is you're defining finer and finer types, which is making your logic more cohesive and less coupled. But what happens is in order to refine in that direction, you get rid of the expensive logic, but now you get redundancy, because across that indicator expression, you're going to have to go copy that redundant code because you have no ability to reuse it among different types. Remember, in abstraction, you're hiding things. And so basically you hide information across within the hierarchy or across the indicator expressions. So since you can't, and so if you refine that and try to make it finer, then you're going to create a massive amount of redundancy. And once you have a massive redundancy, then it's hard to coordinate. And then trying to keep things consistent across the organization and get consistent messages is hard. So you have a bad choice and a bad choice just because you don't have the concept of functional programming or a function. And that's what makes these systems so hard to manage. It's ridiculous. So I think that makes that now. So now let's talk about the abstraction mechanisms within Axis. So Axis is a crazy little beast. Again, it was beta in 1985, and it looks kind of like the mainframes that it probably was trying to replicate back in the day. And I will say Axis, its issue, I will say this. I think Axis was better before the formula tables were introduced and when we had prescribed type of logic, right? You could say this policy belongs to this bucket, so it will be valued this way. And so that wasn't too bad. But once you introduce the formula tables, and especially once you get PBR in, you have a lot more logic. So then you have to introduce this concept of formula tables. So I look at there's two types of formula tables. There's with formula link and without formula link. Okay, and so what happens so when you can look at your types in Axis, like you can look at a cell and it would be like a we'll call it a policy type, right? And then each one of the tables you put, I don't have a picture of it. Each one of the tables that you put in, these are kind of subtypes of that policy type. So you'd have a withdrawal benefit table, and you'd have a partial withdrawal table, and all these different tables. Okay. The problem with Axis is that once you start introducing formula tables, okay, let me back up. The problem with Axis is that all these so Axis is well modularized, but it's not well abstracted with the code. So what happens is you go to program in your formula table, that formula table is very coupled to the object that you use. If you suddenly say, hey, I need to change this object because I need more versatility, now your code is coupled to that object, and many objects are coupled together on how you do it, so you suddenly break a whole bunch of things. So it's modularized, but it's tightly coupled and it's hard to abstract. Now, with formula link, you can abstract better because they give you a couple extra tabs where you can actually do some actual object-oriented programming. And so essentially how you handle that situation is you have to wall yourself off from Axis and code snippets, create your abstraction to deal with all of that stuff, and then have it weave it all back together. So you have to use very advanced programming to come over with the tight coupling. It's not my favorite one. So, and just to be honest, just to be transparent, how I came about this presentation is I'm converting from alpha to Axis, and so I'm having to deal with exactly this issue as I I inherited the valuation model, and I'm trying to keep my pricing model close to my how valuation implemented it, so we can kind of have some transparency as to keeping pricing, understanding our pricing and how we're valuing it. And and I don't have formula link, and it's very hard. Whereas before I did have formula link, and I could deal with these issues much simpler. So again, and the other thing is data link couples your data along with your configuration. So again, that makes it very hard to test. Yeah. Okay, so I've talked about data link and the GUI and the configuration. I've already kind of talked about that. And again, I've already kind of addressed these two as I was on my little rant. So we're going to move on. Okay, so the last one is Atlas. Now, I'll be transparent here. I haven't actually used Axis or Atlas. They came to me and I said, hey, I'm not interested in your software at all unless you can help me solve this problem and that I'm posing to this group. And they said, okay, tell me what the problem is. And so then so we worked together to say, okay, put it in this frame. So one of the things that's nice with Atlas is that, again, it uses XML configurations. So it is decoupling the XML. It is decoupling the data from the configuration so that you can better manage what it is you're doing. So that is a step in the right direction. It also is much like TAS back in the day. So it's built on C++ and it's using, and so all the things you're doing are in a, they try to make it as, they redefine things to simplify it, but basically you can use C++ syntax, which means you would have C++ abstraction, which means if you needed to go bigger and better and abstract things that you could. So this does help solve the problem that I'm trying to address here of having things tightly coupled and loose cohesion. So these are definitely a step in the right direction. So what do I think we need to do to fix ALFA and Prophet? So as much as I was banging on them, I do think they're salvageable, but we got to start introducing the functional concepts into those languages so that we can start managing those at smaller levels, and that would be an immense improvement, because you would immediately see that you would then be able to automate your testing. Hopefully, you'd immediately see the governance footprint of everything that happens around that greatly shrink. To fix access, without Formula Link, I think you're pretty hosed. They have mentioned that they need to modularize it, but I hope they mean to modularize that for the user. But the data link is a very tightly coupled concept with logic and configuration and data. And then I've already kind of told you with the widgets themselves, you've got coupling between logic and data. So it's really got a long way if you're going to get any true modernization and abstraction. Like I said, it's all about modernization, but with the cut, there's no abstraction to be able to help you really deal with that. If somebody knows of a better way, please tell me, because I'm dying for answers. Formula Link makes it tolerable. It gives me ways to do it. And to fix Atlas, now I was impressed with this. This is their own criticism of their own software, that they probably need better transparency into pre-built functions and better visibility for seeing calculations. Now, I will argue that we need to be careful about what we're visible on. So, actuaries have an engineering attitude, and we like to see everything and know every detail, but we have to know which details we need to see versus which ones we don't. So what we need to know is what's called the state space, right? We need to know the likely things that the thing will do in the state space and the behavior expected from it, but we should never be concerned with how it does it. So for example, if Atlas is using a particular array or function or DQ or linked list, and then we go and we say, oh, hey, if we do this, it's going to be faster because I know they're using a linked list, then what you do is you coupled yourself to, even though they've hid it behind a wall and you've coupled yourself to their implementation, and it will make your application very brittle. So you need to know state space and logic behavior, but you should never be looking and trying to understand actually how they implement it and get it done. So what is the end game? And so this is what everybody, so what is the end game? We want to be able to use DevOps tools for actuarial models. There is no reason that we should not be doing that. That is a lack of, like I said, thinking in 1985 and monolithic, not that it's actually practical. That didn't make sense. That it can't be done. So we need to get rid of our large model governance footprint and make it far more DevOps oriented. We need to be able to easily put our our models through a DevOps pipeline and get the immediate feedback. We need to be able to make small changes for whatever what if analysis we need and stuff like that. We've got to get rid of that. And we need to have a continuous delivery of models, and we need to be able to have modern feedback. But more importantly, we need to be able to collaborate. When your data is coupled with your logic, then what happens, you can't collaborate. Have you tried to have 10 people try to do access together? With all the coupling between the data and the logic, the merging is really, really challenging. And same thing with that would be at ALFA and Prophet, because all of those variables, when you go to merge it, if somebody changes a variable you didn't know about, that's going to change your behavior. And so it makes the merging of the model a very single-threaded idea, as opposed to being able to have multiple people work on it together. And ultimately, what we want to do is get to behavior-driven development, where we can have valuation come to the modeling. I don't have time to get into this, but where we basically design our things in terms of features, and we can describe our features in terms of behaviors and scenarios within those behaviors and given conditions on those behaviors. And then behind the scenes with behave, you can actually put code behind this so that we can actually have a good conversation about the model should be working up front, as opposed to trying to build everything off production data and testing very late in the game. We can be testing very early in the game and understanding whether things are going to meet our specifications up front. So, steps to modernization. Change ASOP 23 and 56 to piggyback off IEEE, especially regard the software engineering. Focus on training and upskilling people based on these new standards. Like, again, modernization isn't a technology issue, even though I've been talking about technology issues. What I'm trying to do is make the people more productive, make the people be able to comprehend the model faster, and be able to get changes and understand if they mess anything up faster. It's about the people, not the technology. Then we force our software vendors to fix the front end that the actuary uses, right? I just showed you how to do it with Prophet and ALFA. Basically got to modularize it and give them the functional things, right? And I imagine that I have a high failure rate. Then we need to transform our models. Then we can start putting things through our DevOps pipelines and things of this nature. And so real quickly, these are the resources that I put for this book. This Fundamentals of Object-Oriented Programming is essentially where all the cohesion and coupling come from. That's a fantastic book. When I talked about testing, it's from the unit testing. The Joy of Abstraction is a mathematical representation of what the fundamentals of object-oriented is. That's a Joy of Abstraction is a fantastic book. And so basically these are the ones. And like I said, why do you care about microservices? Well worth a read. If you want to learn how to abstract access later with Formula Link, these are a couple of articles I read for the SOA. Okay. 1 minute left, and I have not looked at anybody in the chat. So you all can unmute. So if you got questions, throw them at me. Oh, yeah. Okay. No questions? Nobody? All right. I know I went through a lot of talk. He's fast.
There's questions in the chat if you want to find those.
Okay. Could you please elaborate on the Python library Lark? Yes. What Lark is a domain-specific language, and it has a transformer in it. I used to have a slide on it, but it was a little bit too much detail. But basically, you come up with what's called a grammar, and that grammar says what is that language? It puts it into a structured tree, and then that you can have Python read that tree and transform it to a new language. So that's literally how I took the alpha and I transformed it into Excel lambdas. The DSLs, it's easier to do a good job at encapsulating the domain or providing insurance abstractions. Does using Lambda make it harder to read sometimes. No, it makes it phenomenally easier to read. I love the lambdas. Everything I do in Excel is lambdas, because as long as you use Excel Labs, you can sit there and write lambdas. You can comment it. You can have functions. You can break it into smaller and smaller pieces. It's fantastic. Highly recommend those lambdas all day long, every day. That's all I do anymore. You mentioned benefits of decoupling, but I'm concerned about network attacks and a monolith or function calls or in memory. Yes, you can get too small, but speaking, we're a long way away from that in our actual software. If that becomes an issue, that's a good thing because we can work ourselves back. But the more is we got to be able to manage and maintain. Let's worry about maintenance first and speed second. Anything else? I think that's all of them, unless people. Yes, yes. If you want to email me, I will be happy to share the slides. Brian_Rubidoux@constellationinsurance.com. You can also find me on LinkedIn. Why don't I just type it in the email, in the chat? That would be better, wouldn't it? And whoever came up with this email address did not have to type it in many times. Okay. So, any other questions? Going once? Going twice? Any disagreements? Anybody think I was full of it? I'll take arguments to the contrary. All right. Well, then everybody have a great presentation. I've enjoyed this whole thing all day and looking at the different perspectives. So anyway, I hope you enjoy your last one. Talk to you later.